Welcome to Breadboarding. This is video 27 in the Breadboard 8088 PC series, PC Compatibility Part 5. We're going to be doing some tidying up of the main board, doing some further BIOS tests, and then adding a PS2 keyboard controller. So I've been meaning to tidy the board up a bit. There's quite a few flying leads, particularly a lot of the I/O and memory, read-write signals, reset button, a number of things have all been sort of trailing across the board quite untidily. So what I've done is I've cut these to size and routed them fairly cleanly, and I've also bundled some of the longer cables together. I've also gone through and replaced individual DuPont connectors for the bus connections with dual pins. I'll show you what I mean by that. And also some of the DuPont cables have been shortened, so sometimes I had a medium length one when a short one would have done. I've also made some changes to the video controller, the monochrome display adapter, in that now the bit that determines whether we use monochrome mode or color mode, I've swapped the values there, so by default it will always do monochrome with 0 and color needs to be set to 1. I also needed to fix a few issues to do with when video enable is set to 0, so it's disabled. Some of the PLDs needed a few updates. I've also temporarily overridden the video enable for getting the BIOS video display working, so when we look at testing the BIOS we'll be able to see some video output. And then I've also going to be going through and testing the various beep codes for when there's a CPU failure, lower 32K RAM failure, and also we'll look at commenting out the keyboard initialization and test routines until such time as we add the PS2 keyboard controller and see if we can actually get some BIOS video output. So this is a view of the board as it's been tidied up. So really what I've done is where there are these sort of connectors down here, a lot of these we're using individual DuPont connectors, and the problem with those is an individual lead can come out without it being very visible. When we've got the double headers here, then it's a little bit more obvious if one of them lifts out, and they tend to keep each other in. I've also replaced a lot of the flying leads, so the leads going all over the place, over here and over here and over here, and so these have now been routed cleanly, and you can see there's a few more bits going up and down the board here. I'll just show you a couple of the changes I did to the PLDs. They're not major. So the attribute multiplexer is the PLD that actually decides where we show the foreground, background, and what colours we're going to be showing. And the changes here, I've changed the black and white colour monochrome sort of selector output from the control register to actually come off the inverted output. So that means that rather than being set to 1 for mono and 0 for colour, then in fact after a reset it will default to mono because it was looking a bit strange coming up in colour all the time for a monochrome display adapter. And I've also added an extra pin on that PLD that allows me, when it's in monochrome mode, to determine whether we show the shades of green colour like an original monochrome display adapter, or whether we want to show the white and grey. And I've also done some changes that when the video enable was disabled, then there were some background colours still coming out for some reason on the display. So we've got the unused pin there now determines the green or white, so default 0 will be green, and if it's set to 1, 5 volts will be white. And then I've just modified the documentation, and then the rules here have now been incorporated, the green and white extra bit and the conditions for no display. So that basically has solved that particular problem. And then similarly for the other video out PLD, we needed to suppress the background. I think when sometimes there was a reverse video, then there was still some background output. So this additional condition. So minor changes, those have been programmed and tested, and those seem to be working. And this is just some of the screens. So this is when the video enable was set to 0, disabled, we're still getting some of these values, and even after one of the PLDs has been updated, then we're still getting this. So with those two PLD changes, it's basically got rid of those screen artifacts, and it now will be completely black when video enable is set to 0. So let's take a look at testing the BIOS. So within the BIOS, in the early part of the startup, it actually tests the CPU features, so it tries a lot of the flags and moves values around the registers. If there's a failure, then basically it'll output a continuous tone. And so all I've done here is we're just going to comment out the correct test and comment in an incorrect test. So this would effectively simulate a CPU failure. We just go and assemble this. Okay, so that's assembled. What I'm going to do, I'll speed this up because downloading this can take a little while. In fact, what I will do is I'll also hook up my slowest of my logic analyzers. I'm going to put this on the power on self-test port over here. So I'm just going to fix that up and start up logic analyzer, and then we'll download the BIOS. Okay, so I've fitted the logic analyzer and I've got the post configuration here. We can run this in the background, and then when we actually start running the BIOS, then we should be able to capture what messages and things are coming out. Okay, so I downloaded the BIOS. I've loaded it in the correct segments. We're just waiting for this. So I'm just going to run it. You should hear a continuous tone. You should be able to hear the background noise. You can see here that the post codes, we've got 01, then 52. So if we have a look at what 52 means, and if we look in the error include file, we should be able to find, there we go, we've got eCPU fail. So we'll comment that back out again and put in the correct test. Then we'll go down to the next one. So the next one is actually testing the first 32k of RAM, and basically if the first 32k of RAM is faulty, then the BIOS can't really do too much, so it gives a beep and doesn't do much else. So again, all we're going to do is to comment out the correct test, put in a fake test, and what we should then get is a different set of beep codes. So this should be beep, pause, I think. So just rebuild the BIOS. Again, I'll download it and run it without recording that bit. Okay, and we're ready to run this next test. This should be the lower RAM failure. And that's doing an intermittent beeping. And we can see here that on the power and self test, we've got 1, 2, 3, 4, and then 54 is the error code there. And if we have a look at what the code 54 stands for, we can see that low RAM fail. Let's go back and put those in, back in, comment out. So the next stage in the BIOS startup, when we tested the BIOS in the previous video, then obviously it was failing on the keyboard initialization, and the reason why it did that is because we haven't got a keyboard controller at the moment. So for the moment I'm just going to comment out the keyboard initialization and we'll see how far this then gets. Okay, so we're ready now to test the BIOS with the keyboard controller initialization commented out, so just press 0. In actual fact, the tone that we got there was a startup tone, which sounded a lot more hopeful. So if we have a look at what the remaining codes mean, so we're really looking at 678 all the way up to 30. So we can see we've got initialize the timer, initialize the interrupt controller, so we're not initializing the keyboard, enable interrupts, locate video BIOS. I don't think it did locate a video BIOS, 12, 21, 22. So 12 indicates no video BIOS using MDA CGA. There's no initialization of the real-time clock because we don't have that. Detect CPU, detect floating point, detect serial ports, detect parallel ports, and then start a RAM test. Now it hasn't come up with RAM test complete, but it has actually got a fair old way. So that's looking quite reasonable. So if we have a look and see where the next step after this would be. So this is where it should start to initialize the monochrome display adapter. Now the only issue at the moment is we don't have any way to tell the BIOS at the moment whether or not it's using CGA or MDA. So what I'm just going to do is to comment out the bit here to cause it to actually go and initialize the video, and hopefully we should be able to see something on the video display when this starts up. So we'll just reassemble that and I'll download this, and then we'll look at the video display when this starts up. So I ran up one of the test programs earlier, so this is just showing the MDA with the green mono output. I'm now just going to run the BIOS. And in fact, we have actually got some video output. Now, the only problem is it's difficult to actually see what it is because it's all mixed up with there. So I think what we'll do is we'll just do a modification of this test program just to clear the screen, but leave it in this green mono mode. So here's MDA test 10. So this is just a modification of the previous one that we were using to generate that pattern. And this sets the display to MDA green and clear screen to the BIOS. So we've taken out generating a lot of the test patterns, and the only thing I really had to do here is that I was finding that the color palette was getting corrupted, and so what I ended up having to do is to put a short delay between writing the red, green, blue, in that some cases the green value was ending up in the blue value as well, which was causing some strange effects. So all I've done is added a bit of a delay between the writing each of the red, green, blue, and that seems to have solved the problem. The output here is our CRT control register now for the black and white bit 1 is now 0. With the change I've done, that now means that mono is 0. So it means that when the PC resets, then it will automatically be set to mono rather than to colour. And then we clear the screen and it still is doing the post output, but other than that, it's the same as what we had previously. So I'm just going to download that and run that. Downloaded that, let's just have a look at the video capture and just going to run it. And that has obviously cleared the screen, so that's great. So now all we need to do is to download the BIOS again, and we'll run that again and see if we get a cleaner output on the display here. So download the BIOS, I'm now ready to run it. And we get the startup beep, and it's also testing the RAM and attempting to boot the OS. But of course we don't have any disks or any way of booting the OS at the moment, so we're just getting the boot failed, press any key to try again. But that's looking quite promising. We've got our Breadboard PC 8088 BIOS, copyright Sergey. The main processor is a 1981 or later, so I know that my chips are something like 83, I think they were. Now the issue here at the moment is it's saying the display adapter type is CGA. Now at the moment we know we've got an MDA adapter, so I suspect that some of the video detection for the configuration needs to have a pin on the keyboard controller, which I think the XI8088 used to switch between MDA and CGA. And we can see at the moment we don't have any serial ports, parallel ports. It's configured to default to 2 floppy drives, 1.4 meg floppy drives, and we've also restricted obviously it to 256k of RAM because we've actually loaded the BIOS in RAM at the higher part of the memory. But that's actually looking pretty promising. And if we have a look at Logic Analyzer output, I did need to extend the time for the Logic Analyzer to be a bit longer because the boot failure takes a number of seconds. So if you have a look at Logic Analyzer now, we can see after the 30 that we had previously, we've now got 31, 40, 43, and then 0. So if we go and have a look and see what that means. So 31 means RAM test completed, 40 scanning for BIOS extensions, 43 I think is BIOS extensions complete. Yep, BIOS extensions complete. And then 0 I think is what we actually get when it's trying to load the operating system. Yes, eBoot is booting the OS. So in fact it's gone all the way up, all the way through the BIOS, all the way up to trying to boot the operating system. Once we have a floppy disk controller with a bootable floppy disk in it, then obviously this would be then when it would start to kick off and boot the operating system. But this looks like it's all working as much as we could, and obviously once we've added the keyboard controller, then hopefully it will be able to determine what type of video adapter it is, and it should be able to initialize that cleanly. So now we're going to have a look at the PS2 keyboard controller. Now the Nanocomp 6809 Video 18 includes a lot of the background on PC keyboard, so I'm not going to repeat a lot of that. I'll include a link on the top right hand corner above on the screen at the moment, and also down in the description below. So if you want to have a bit more of detailed background to the keyboards, then please go and look at that video. I'll cover some of the high level points from that video here. So I really want a standard 102 key keyboard. Now modern USB keyboard needs USB drivers and probably modern microcontroller, and I'm trying to do this using 1980s and early 90s components where possible. Now the original PC, PCXT and PC80 keyboards are quite difficult to get. Probably is possible, but I'm not that fussed about getting original keyboards here. But what you can still get is IBM PS2 compatible keyboards. Can still get those for about £20-25, $30 on Amazon. If you want to know more about the low-level PS2 keyboard data, then Ben Eater has a number of videos on this, and so this is partway through Ben Eater's video where he actually shows how to look at the signals coming back from the keyboard. So there's the clock and the keyboard data. The main thing you do need to know about in doing this is that you need pull-up resistors to 5 volts if you're trying to look at the keyboard clock and keyboard data. And this covers all the low-level signals, timing, scan code, so I'm not going to go over that again. And in the video 18 above here, I also include how to use Logic Analyzer to look at all the scan codes and things like that. So the model that we've been working with, the PCXT, is the 5160, IBM 5160. The original PC had an 83 key keyboard with a larger 5-pin DIN connector. Still very similar keyboard was used on the XT. The AT introduced an enhanced keyboard, 102 key keyboard, but still with the same 5-pin DIN connector. It changed to use a different keyboard controller. When the PS2 Model 80 came out, then this had the enhanced keyboard, but it also had the PS2 6-pin mini DIN connector. So what we're going to do for the Breadboard PC keyboard controller, we're going to use a standard PS2 keyboard with a 6-pin mini DIN socket. Now the original designs used an Intel 8042 microcontroller, which had the keyboard BIOS built into it, but these are difficult to find. I haven't tried too hard, but I was able to find the VIA VT82C42N. It's a 40-pin dip chip keyboard controller, and I was able to get these for about £3 to £5 on eBay. From the actual data sheet, it says it's a compatible direct replacement for the Intel 80C42 BIOS version of the keyboard controller. It's fully implemented in hardware logic, so it's very fast for any command, and it can work with both the PS2 and the original AT configurations, and has the PS2 mouse support. And the pin out here is looking into the socket from the front. And the main thing that when I was first experimenting with PS2 keyboards, you need to include a 10k pull-up resistor to 5 volts for both the clock and the data line if you're trying to see any signals on it with a logic analyzer or an oscilloscope, because they are open collector outputs. They won't actually generate a signal otherwise. So let's have a quick look at the schematic for the keyboard controller. I've moved it to the top left, where it's going to be just the left hand side of where we've added the post port timer, interrupt controllers and the DMA. Basically we've got the 8242 keyboard controller chip, we've got an inverter, we need a crystal oscillator for this, and the key thing about these inverters, it's open collector, and we need to have the pull-up resistors for each of the outputs and the capacitors as well. I've made a special mouse and keyboard DIN 6 sort of Vero board connector to plug into the breadboard here. We just need to be careful when wiring this up that we make sure we refer to the port number rather than the pin number. So when looking at P22, that's actually the label on the chip, not pin 22. So I have made that mistake in the past. And when we come to look at this, there's a couple of feedback loops. So test 0 goes to the keyboard clock, test 1 goes to the mouse clock, and then there's 2 data inputs. So P10 comes from the keyboard data and P11 comes from the mouse data. So I'm going to put this over 2 breadboards. The reason being there's quite a lot of wires that go from here over to here. I've got the data and the bus connections over here. I need to fit a crystal in around here somewhere, and then most of the connections are going to be going to these 2 ports here, and I have done a pin out here. So this connector is similar to what I did in the nanocomp video, so it's basically a little bit awkward because these DIN connectors actually have 2 pins fairly close together, so we need to actually cut the tracks where these are and then put links around. This basically provides the ground, clock, data, not connected, then 5 volts. What I'm going to do is to speed this up and commentate over it, so when we come back hopefully we'll have all this wired up and ready to go into the PC and see whether we can get the keyboard to be recognised by the BIOS. Okay, so just plug all of the chips in and put in the power lines for each of the chips and for the PS2 sockets there. Put in the decoupling capacitors. Now we're going to put in the 8 MHz crystal and the 2 capacitors for that. There are a couple of lines there need to be tied to 5 volts or to ground, then all the others will be wired in later. So now we're going to do the keyboard clock and the keyboard data, and then the pull-up resistors to 5 volts. Just put those in there. In fact, I decided to use white for data just to make it a bit clearer. So now that's wired up to the PS2 keyboard socket. Make sure the power for the keyboard socket's put in, and just make sure the data and clock signals are also in there. Put in the capacitors there. That should all be everything apart from the feedback for test 0. So this particular line is correct, but this one is incorrect. In fact, that should have been a white one going down to the mouse. So I need to correct that later. So this is the output for the data and the keyboard for the mouse. I'll just wire those into the socket. Those are the pull-up resistors. And then we just need to sort out the capacitors. So we're just going to wire in the 5 volts and ground connections for the mouse port. And then we'll just move those over so we can bring the clock and the data signals over to the right hand side to put in the capacitors. Now we just need to tie a couple of leads there to 5 volts. Now pin 16 is our video mode. This needs to be set to ground for MDA monochrome display adapter. Okay, so this is all now wired up, and I've got some DuPont cables to connect it up to the rest of the system. But we'll probably run out of time now for testing this and installing it with the rest of the PC. So I'm going to break the video now, and in the next video what we'll be doing is plugging in the PS2 keyboard controller, testing it with the BIOS, and seeing whether or not we can get any keyboard output on the display. If you don't want to miss out on future videos, please hit subscribe, and if you can just hit like, it just helps to make the videos available to more people. Thanks for watching.